All right, so our next speaker is Peter Bloem. He'll be talking about universal pre-training. Yeah,
Right.
thank you.
Let me put this in full screen. You still see the slides online?
Yes.
Okay, great. So, yeah. Hi, my name is Peter Bloem. I'm going to start with an admission, which is that this work, I'm going to present this work as a follow-up to what Tim just presented, but actually a large part of it was done in parallel and I was scooped. Scooped by about 1.5 years, so I don't really have cause to complain, but basically what happens when you get scooped is you figure out what's still new or what's your jumping off point and you make that the paper. I mean, it's happened to all of us. And so that's basically the bit in black is what I was going to call my paper, Universal Pre-Training, which is basically for a large part what Tim already presented. And then what's written in sort of handwriting is how it differs and what's still new compared to what you've just heard. And I'm telling you this primarily because there's a couple of places where this work, basically, if I present it as a follow-up to what Tim just presented, you might ask, well, why did you do this so differently? And why didn't you use that baseline? And why didn't you use the same? That's all on the to-do list ever since I found out about this paper. So if you're wondering why there's some differences, that'll be why. It's a talk in 3 parts. So we'll do a little bit of intuition first. It chimes with a lot of stuff we've already heard, what Marcus already presented. But just sort of giving a slightly different perspective on this notion. Then we'll go into some theory that we'll need to justify the slightly different way of doing things that we have here. That'll probably be the bulk of the talk. And then we'll go to some practical experiments in the end. So for intuition, I really like this. I took this from Cover and Thomas, the famous information theory book. It's this intuition about the monkey behind the typewriter. We all know the monkey behind the typewriter, right? If he lives forever and he bashes keys at random, then after some finite amount of time, he will have typed out the completed works of Shakespeare, together with some astronomical amount of other stuff. What people don't often talk about is what happens when you put a monkey behind a computer. And because of all the stuff we've heard so far, which is that the collected works of Shakespeare have a certain regularity and you can exploit this with compressors, this monkey is actually going to type out the collected works of Shakespeare faster than the first monkey. Because the first monkey needs to be lucky enough to get every single character of the collected works of Shakespeare right, whereas this monkey only needs to be lucky enough to type out the shortest program that produces the collected works of Shakespeare. So by that difference, this monkey is going to get there a lot quicker than the other monkey. Why is that relevant? Because it tells us that taking random noise, i.e. a monkey, and passing it through a computation, even a random computation randomly chosen by the monkey itself, gives you richer or gives you a better chance at getting richer information. Basically, if you put the monkey behind the computer, you get a higher chance of getting the collected works of Shakespeare. This is all very vague, but I'll try and make this more precise as we go along. But basically, this is the key idea. We take random noise and we pass it through a computer or through a random computation. We get more valuable noise. And so here you see at the top, there's no typewriter emoji, but this is a monkey behind a typewriter. What you get is a uniform distribution, sort of sampled IID over the characters of the keyboard. Whereas if you put the monkey behind a computer, you still get very random noise, but the noise has structure, right? So you have B in this, this sequence over here, B recurs a lot. And then in this sequence over here, you get T recurs a lot. And basically, if you look at the start of the sequence in these last 3 sequences, it can help you predict what's going to happen at the end of the sequence. Whereas in the first sequence, there's no prediction from the start to the end. In the other sequences, there is some pattern between the two. That's basically our fundamental sort of jumping off point. And so the idea just is sort of in very high very high level, where we're going to go is that we're much like Tim's story. We're going to generate this kind of data, and we're going to train a large language model on it. The idea being that any structure the large language model will spot that is specific to any of these strings, like the fact that B is very frequent, that's going to disappear from one sample to the next. So the model may very briefly learn it, but then it has to forget it immediately because it's not true for the next sequence. But any patterns that are common to all sequences, like the fact that the beginning is predictive for the end, or the character frequencies at the beginning are likely to be predictive for the character frequencies at the end, that's going to some extent to recur from sequence to sequence. So that's going to be something that the model picks up on, learns, and remembers. All right, so we need some theory to justify all of that. And we've heard most of the theory already, so I'll sort of go into why, basically what we do different from the previous paper and then from Solomonoff induction in general. The step one is we use a slightly different flavor of Turing machine. So what you see here on the left is the monotone Turing machines that are common in Solomonoff induction. And basically the way they're formalized is that you have your input tape, you have your output tape, and they are one way. So as soon as the model has, as the TM Turing machine has read one cell on the input, the head that reads this input tape can only move to the right. It can only read further bits, but it can never go back. And the same is true for the output tape. Once it has written an output, it has to keep going. And this is very good for distributions on infinite sequences. So you get infinite bits or arbitrary number of bits on the input tape, and you just see as time goes to infinity what happens on the output tape. And it's very good for sequential prediction. So given what we have done so far, what's going to be the next character or the next bit that this TM spits out? So this is a very natural fit for the way we train large language models, this autoregressive stuff. But there is an alternative, which is the prefix Turing machine. And really the only thing we do here is that we allow the output to be two-way, but the input is still one-way. So if we're doing this in bits, we have a one-way infinite or arbitrary length input tape, and the model is only allowed to read from left to right. That's never allowed to go back, but it is allowed to go back and forth on the output. And this is very suitable for distributions on finite sequences, or it's used at least for distributions on finite sequences. And it's better for sort of predicting the probability of a whole object. So instead of sequential prediction of infinite strings, we have a finite string representing some object, and we want to say, what is under my probability distribution represented by this Turing machine? What is the probability of that X? And so on a prefix Turing machine, you can build Kolmogorov complexity, maybe these days the most popular form of Kolmogorov complexity. You just grab a universal Turing machine, which enumerates, basically takes an enumeration of the prefix Turing machines, and if I give it inputs I and Q, it simulates what happens when I take Turing machine I and run Q on it. And these are all prefix Turing machines. And then the Kolmogorov complexity is just the shortest program for my X on this universal Turing machine. And the reason that these universal Turing machines, or these prefix Turing machines, sorry, are so useful for modeling probability distributions is that basically if you look at what happens for every input, for every bit you put on this input tape, you can see that they form very naturally, or they define a prefix tree. So either if I give it let's say a 0 on its input, it either keeps computing and at some point moves to the next cell, so asks for another bit, and I can give it a 0 or a 1, or it stops computing and prints out something on the output tape, or it goes into an infinite loop. But let's not worry about that here. So you can sort of draw for all the possible inputs what happens at each point, whether it asks for another bit or it spits something out, or we actually have here a non-halting state. And what you see is that you get a prefix tree, right? That's why they're called prefix Turing machines. You get this tree of all the outputs that the Turing machine can give you. And this is very naturally a probability distribution because I can just follow the tree and at each internal node flip a coin, whether to go left or right. And then when I get to some output, that's what I've sampled. So then I have a probability distribution. And then the probability of that probability distribution is just 2 to the power of, for all the programs that produce some output, 2 to the power of 2 minus the length of those programs all summed together. So this is what I mean when I say, you know, these prefix Turing machines are really useful for modeling objects, distributions on objects. Something I presented 3 years ago at the first AIT symposium was class-bounded Kolmogorov complexity. So this is interesting. Also, if you're interested in approximating Kolmogorov complexity, basically what you can do is you can pick a subset of all of these Turing machines. Instead of considering all of them, you only consider the ones that model Markov models or VAEs or diffusion models or some bigger class, all polynomial time TMs, and you take that subset, you call it C, and you assign some prior probability C to every Turing machine in your subset. And then you have this mixture probability MC of X, which is just a mixture with this prior over all the probabilities that you get from all these Turing machines. That's what we call class-bounded Kolmogorov complexity, and resource-bounded Kolmogorov complexity is a special case of this. And you don't lose that much. You lose a few things. One is this invariance property that you may know about Kolmogorov complexity. But what you get in return is that if all the C's in C are relatively well behaved, so they're not too weird and they don't do anything like going into infinite loops, then MC is computable. So that's a very nice thing to have in Kolmogorov land. And it's what we call a safe approximation. So if you compute your class-bounded Kolmogorov complexity and your X comes from C, was generated by a model in C, then you know with almost certainty, or no, I shouldn't say almost certainty, but with decent probability that your class-bounded Kolmogorov complexity is the same as your approximate, is the same as the real Kolmogorov complexity. And it's basically the probability that they differ decays exponentially. Interestingly, this doesn't work so well for the normalized information distance. So I've never quite understood why normalized information distance, since we're talking about that today, is actually so well approximable. Because a lot of the approximation results about Kolmogorov complexity sort of disappear or get very difficult once you start talking about normalized information distance. But it does work in practice. So that's, if you're interested in NID, then that's actually something interesting to look into, but it's not what we're talking about here. What we're going to do is we're going to look at this MC. So the reason I'm introducing this is nice to have, is that we can now talk about any kind of class of probability distributions that we like working with, like VAEs, like Markov models, and treat them as approximations to Kolmogorov complexity. And there's really only one property we need that we're going to use going forward, which is the property of domination. And we say that one probability distribution dominates another probability distribution if it assigns higher probability than the other one. So P dominates Q if P assigns a higher probability to every X than does Q, up to a scalar constant, multiplicative constant, which is always a bit sort of counterintuitive to think about. So it's better to translate it to bit land, to compression. So if you take the negative log probability of a probability distribution, you get this. This is basically a representation in bits, a compressor in bits for any computable probability distribution. This is a compressor. We can represent X in this many bits. And so then we say this compressor dominates this compressor if it can compress better than Q up to some additive constant. So this is the basic property of Kolmogorov complexity. And just if you move to probability land, the plus C becomes a time C, and it all becomes a little bit less intuitive, but that's basically what we're talking about. And so we say that mx, which is the probability distribution you get from the whole class of Turing machines, the universal distribution, dominates any computable distribution. That's a foundational property of Kolmogorov complexity. But we can also say that mcx dominates any distribution in cx. These are all fairly straightforward results. I have one domination result here just to illustrate the idea, but I need to hurry up a little bit, so I'll skim past the details, but basically to illustrate how this works, you can say something like, if I have model classes C and D, if D contains some specific Turing, if D contains a universal Turing machine for C, so a Turing machine that simulates everything in C, then we can show that this mixture distribution over D dominates C, so it dominates every probability distribution in C. So in a very real sense, you get this kind of hierarchy where D is higher in the hierarchy than C. So this is sort of the way you get out of the things like the no free lunch theorem in Kolmogorov land, where people say, well, you have to fit your model to the task. We can actually say, well, so long as you make certain assumptions, you get a hierarchy of classes, and up to this constant that you get for domination, D, if you can compute it, is actually a better model class to use than C. Nope. So with that, and focusing primarily on this notion of domination, we need these three results to get to our practical section. The first is we need to show that Solomonov induction also works with prefix TMs and under class bounds, which actually, it turns out, it's the proof for Solomonov induction just works if you translate it to the setting, so you can just use the same proof. And that's basically going to justify that we're sampling from a prefix TM rather than a monotone TM. Then we are basically going to look at this idea that random computation enriches random noise. So we're going to make that more precise in this language of domination. And we're going to add iteration. So we're going to say, not only can you make noise better for learning from by passing it through a random computation, if you take that better noise and pass it through another random computation, you get even better noise, and so on and so on and so on. And if we do this carefully, we can actually end up with a hierarchy that ends up with the universal Turing machine, or the universal distribution. It's not guaranteed. You can also stall somewhere else, but you can do it carefully, which is what we're going to do. And here we move into the world of practical stuff. We are going to sample random LSTMs, which are not so popular anymore, but still used. And we are going to use those as our random computation. We sample a random LSTM, we feed some noise through it, and we sample from it. And if you iterate that, we will show that converges in some sense to the universal distribution. And the nice thing about this, compared to working with actual Turing machines, is that we have a lot more hardware support for LSTMs. You can do a lot more computation in the same time with LSTMs because you can run on the GPU. And so this is the benefit of this class-bounded view, where we can move to any model class that we like. And so we're going to pick a model class that suits our purposes, and then we can run on the GPU. All right, so first we move to this Solomonov induction, but in the setting of TMs, of prefix TMs. Basically, we need to define what it means to do next bit prediction, sequential prediction in this prefix setting, where we only have probability distributions over whole finite strings. And basically, we define this probability distribution, where basically we use this notation to say this is the set of all strings that are prefixed by X. So this is not a string, this is a set of strings. And then P of that set of strings is well defined, because that's just an event, so you can ask for the probability distribution of that set of strings. And then the conditional distribution of observing the bit B given the string X is just the probability of observing xb, the prefix xb, given that you've already observed x. So it's just pure language, pure probability theory, basically, just the basic principles of probability theory. I think you need to allow 3 values for b, so you have 0 and 1, but it could also be, because these are finite strings, that the Turing machine just stops after x. So you need to allow for that. All right, so if we do that, then what we can define is first of all, the KL divergence between 2 distributions, P and Q. So if we have P and Q conditional on x, what's their distribution on the next bit? Some KL divergence, and we can take the expectation of that KL divergence for a given length of prefix. So for some length of prefix, let's say prefix of 3 bits, we take all of these KL divergences for all possible prefixes, weighted by the probability that we see that prefix, and that we call dn. And then what we can show, and this is really just the Solomonov proof, is that if Q dominates P, then the sum of all of these dn values from 1 to infinity is bounded. So over all of these prefixes, so if you imagine sort of observing longer and longer strings, in the limit of long strings, over all of these prefixes, if you sum up all these KL divergences, this sum is going to be less than some constant. And that's basically your Solomonov result, slightly abstracted to having just one distribution that dominates another distribution. Here we go. But basically this says that, yeah, if you just observe more and more bits, eventually these two will agree. Predicting by Q is going to be just as good as predicting by N in the expected KL divergence per bit. So it's a constant, so as N goes to infinity, the proportion will disappear. So this is the basic Solomonov result, and it holds just for any 2 distributions that are where one dominates the other. Yeah, go ahead.
Because you're using P margin of x, and then this conditional, so that conditional distribution is side of KL, they're arbitrary, or?
Yeah, so it's the KL divergence on the sequential predictions. So you have this P and Q give you a sequential prediction on what's going to be the next bit B once I've seen a prefix X. And those 2 distributions we compare to each other, right? So you can compare according to P or compare according to Q. And then the KL divergence basically tells you how much you will regret using Q instead of P.
Oh, that's clear. What I'm asking is like the margin of px, you obtained it from like the distribution in the first slot of the KL or in the second slot?
Yeah, so P is a distribution on finite strings. So this is the distribution on all strings that have this prefix. The probability summed over all strings that have this prefix. So this is what's defined. This is what the prefix Tm gives us, is a probability on finite strings. And then we define the conditional distribution in this way. Does that answer your question? A Q is the same kind of distribution. It's also a prefix Turing machine.
P corresponds to the true distribution, which I do not know, and Q corresponds to the Solomonov distribution. But in this case, it is just any distribution which dominates the true distribution. Solomonov dominates, but this is more generalized. It's just,
Yeah, exactly. So for the Solomonov result, you would fill in m of x here and any computable distribution over here for P. So that basically gives us license to do this to do this Solomonov idea from the previous task with also with distribution, with any kind of distribution, with any kind of model class. So long as we have this domination result, then we can say, well, we're going to sample from this, and then we're going to test if our predictions are as good as if we had predicted from P. So then we go to this enriching noise by iterating random computation. Oh dear, I'm running very late. Basically, the way we do this is we add a conditional tape to our Turing machine where we can add some conditional information that the Turing machine can also use, which just gives us a conditional distribution, which is conditioned on Z. And then we define M0 as some kind of uniform random distribution. And we're going to create a hierarchy of M1, M2, M3, where Mn plus 1 is the distribution we get by sampling some random noise from Mn in our hierarchy. We sample a random model from the class prior, and then we sample our new string from this conditional distribution, where X is what we sample and Z is what the sort of noise that we had from the previous layer of the hierarchy. So what we get is this sort of hierarchy of distributions we can sample from. And what we can show is that each level in this hierarchy dominates the previous level in the hierarchy. So if we do this for n plus 1 times, the resulting distribution dominates what we get if we do this for n times, so long as the identity function is in our model class, but that's a very simple function. The proof, I don't have time to go through it, but it's in the slides. And it's basically rewriting. So you just fill in your definition. You eliminate some stuff, you eliminate some terms from a sum, so you get your inequality, and you end up with the definition of Mn, which basically proves that if we do this n times, we get sort of better and better distributions in terms of these in terms of this domination. That doesn't mean that we converge to the universal distribution, but we can show that if we pick the right model class, in this case LSTMs, that we do. So we converge in the sense that basically what we can do is we can have these LSTMs simulate one step of the UTM. And so what we can say then if we do this iteration n times or n plus 2 times, then we dominate the distribution that we get if we run the UTM for n times. One caveat here is that the constant of domination does grow in n, so you don't actually get what you can get is an approximation of the universal distribution with a finite constant. But I think for now this is a reasonable enough way to do it, and probably we don't really care about that kind of approximation, at least not in this stage of the process. I've left myself about 1 minute for the results, but basically we now have everything we need to. Okay, thanks. Okay, oh yeah, we have a break afterwards. Well, apologies for eating into your lunch. So, but this is the basic idea, right? So we now have an idea of a way of simulating random, of getting this random noise. We get some random noise, we pass it through a random LSTM, and then we get that noise and we pass again through a random LSTM, and so on and so on. That gives us rich noise that we can pre-train a model on. And so what we do is we get a bog standard autoregressive transformer, GPT style, and we train it on that kind of noise. And then as we train, we're going to check the zero-shot performance on Wikipedia. So how well does it predict Wikipedia without ever having seen it? So the first time it sees Wikipedia is in its context, and lots of other data. So there's a small problem. If we do this in batches, then we get a bunch of samples from the same LSTM, whereas we want IID samples from this distribution. So we want different samples from different LSTMs. And another problem is that this cost of iteration grows linearly, of course, the more we iterate, which we don't like. So we have a little trick to avoid these two problems, where basically we buffer. So we get a buffer filled with noise. So these rows are instances in our buffer. so instances of sort of random characters. Starts as random noise. What we do is we slice out a batch of random rows of conditional informations and small seeds. We feed that through a random LSTM. So we put the seed at the start of the sequence and we feed the conditional as additional information. We just concatenate these two. These are, we embed them so that they become vectors and we concatenate them. And then we pick our random LSTM and we sample one character at a time, autoregressively. And so these result sequences that we get, one for every conditional information, we replace the original conditionals that we sampled by these sampled sequences here. And then we slice some other random rows from the batch to train our transformer on. And basically what this is going to ensure is that with decent probability, these instances are all going to have come from a different LSTM. So we get rough IID-ness in our batches, which is nice for training. And if we repeat this loop a bunch of times, so we do once the thing on the left, then the thing on the right, and then the thing on the left, and we iterate that. After a while, all these rows are going to have passed through multiple LSTMs. So we get this iterative property more or less for free. We only have to run one LSTM every batch, but still our instances have been passed through lots of different random LSTMs. And so here's the result on Wikipedia, specifically the Hutter Prize data, the original one. And basically, so what you're seeing here is instances seen is the number of instances of the original, of this random data that our model has observed. And this is the loss in bits per character, so the predictive regret or the predictive accuracy of a slice of Wikipedia, basically. So we train a model on 256 characters so that we can fit ASCII in there, and then we just interpret Wikipedia as ASCII. And so this is all zero shot, right? So as it trains, every 100,000 or so instances, we test its performance on Wikipedia. The dotted line is what you get with a Markov model with hyperparameters fine-tuned. So this is one of those places where I should have used the CTW, would have been much cleaner, but this is just a good Markov model. And so it dips well below that, which is not that exciting, perhaps, in terms of real practical use, but it shows that the model is really doing something useful. And what you see here as well is that we train models of different sizes. This is width and depth. So we're going a little bit bigger in model sizes than the previous talk. And we are seeing some scaling behavior here. So things get better as the models get bigger. Not really proportional to the amount of money you're spending on training, but it shows some it shows some benefit to scale. So there might be some kind of scaling law here if we look harder. And so here are the other data sets. We have sort of a nice selection of different things. What we see rather surprisingly is that real world data works pretty well and it beats this Markov baseline on German text, Wikipedia data, and code. This is JavaScript code. But if you set up artificial tasks, I think this bits flip is one to focus on, where basically we sample some random bits, then we set that we give it that sequence, but flipped around, as in mirrored. And then the same thing again and again and again. So you should be able to predict, if you understand the program, you should be able to predict this in 0.5 bits per token per bit. Not only can the model not learn how to do that, so it doesn't spot that pattern, it doesn't even do better than the Markov model on this kind of data. So this is really, yeah, we're not there yet. These kinds of problems, these are, at least for this model, too difficult. We can then, once we have our model, we can fine tune it. So we can say, Oh, sorry, maybe one quick point. Oh no, sorry, that's in this slide. We can fine tune it. So we can say we've pre-trained on all of this noise, randomly generated noise. Now we show the model Wikipedia. So here, this is a little hard to parse, but you see over here a model fine-tuned on the Wikipedia data and tested on the Wikipedia data. That's the orange line over here. The dotted line is a baseline where we just take the model and we reset its weights by the natural initialization. And the bottom line is the pre-trained model. So you see that it drops to a performance of 1 point something more quickly than the fine-tuned model. So this is sort of up to here. This is what you save by using this model that's been pre-trained without seeing the data. There's lots of caveats here. If you tune the learning rate better, you have to stabilize the models a little bit, but the difference gets smaller. So don't read too much into this, but it's a yeah, it shows that at least in some settings there seems to be a benefit. I think the more interesting results, and this comes back to what Tim was asking about, is that on the other data sets, so if you keep looking at the orange lines and you look at something like NDFA, as you train your baseline model on Wikipedia, it's slowly, this is just some deterministic, non-deterministic automaton. Your baseline model is slowly going to learn some prediction on this non-deterministic automaton. But the pre-trained model doesn't really lose its performance. So it retains its performance on this NDFA. And the same thing here, as it trains on Wikipedia, it doesn't lose its pre-trained performance on German, and it actually gets a little bit better because there's some overlap there, same on code, stuff like that. So this isn't a sort of be-all and end-all of generalization, but we're seeing some generalization benefit to pre-training in that all these other tasks that it has learned during pre-training, it remains capable of doing them. We have some ablations where we show, so the dotted line here is the final model that I've just explained. We show that if we take this iteration out of it, or if we take this buffer out of it, it gets a little bit worse. So it is worth it, all of the stuff I was talking about. I think this is interesting. So this is literally the UTM from the previous talk. With its resource bounds multiplied by 10, 15, and 50 and 250. So 50 takes slightly less long to sample than our one, and 250 takes slightly longer to sample than our one. And what we see is that with this UTM, and again, caveat, this is pretty much transplanted right away, so maybe I did something wrong here, but what we see is that we lose this monotonic convergence. And also we don't get a monotonic improvement in the resource bound. So the 250 is in the middle between the 50 and the 10. And I think that what this shows is that the model requires a certain amount of curriculum learning. So probably these are all more interesting and more sort of better to train from. But actually, the model needs some simple data mixed in as well. The model needs some constant data and some noisy data. And my guess is that that's what it's getting from the LSTM. So I'd really like to try a mix of both, but that's on the to-do list. All right, and skip a couple of things and change maybe on one point of thing that I think it might now be time to start thinking about. Basically, there's no real guarantee that any of this is going to work at scale yet, but it's sort of beginning to paint a picture, right? That we might be able to trade off data for compute. By investing more compute, we can use less data. This seems to be like this might be possible using this kind of scheme, which is worrying given where large companies are now going, basically giving up their carbon neutral promises and reopening 3 Mile Island and stuff like that, all for more AI, bigger models. So I think it's time to start worrying about that a little bit, that this might be pushing things in the wrong direction, but it might also be pushing things in the right direction in that if you train these kinds of models, they are of general use. right? You can train one of these models. If it really works, anybody can use it for their specific task. So it might be good to, if we start training these models at scale, it can help with this problem of energy use, so long as we make the model public. That's really all I'm sort of advocating here, that at some point, as we do this, the model should be made public so that the energy invested in the model training can be recouped by everybody with a downstream task. All right, I've gone way over time, so sorry for that, but that was my story. And I don't know if there's still time for questions, or maybe we do that over lunch.
That's fine. Next speaker.
Okay.